My name is Jeffrey Frankel, and in this series of YouTube videos I will show you techniques and tips to reduce the time it takes to deal with questions in paper 1 of the IB chemistry exam at both standard level and higher level. As soon as you see a gas, pressure, volume, temperature in any question, immediately think of the equation PV equals nRT, where P is pressure, volume, V is volume, N is number of moles, R is the gas constant, and T is temperature. So, first of all, P. Generally in this equation, P is in pascals, that's fine. Volume. Now this is interesting. Volume is usually in meters cubed, volume is usually in cubic meters, and they give you this very strange given fact, which to me is a little bit confusing. I prefer to see cubic meters as 1,000,000 centimeters cubed, or 10 to the 6 centimeters cubed. They've said 1,000th of a cubic meter is 1,000 centimeters cubed. Well, if you like that, fine, but I personally prefer this. And they've also given you the gas constant, which is very nice of them, 8.31, which is the normal value in joules per Kelvin per mole. You look at the temperature and you know it's not centigrade, it's Kelvin. So you add 273 and you get a T of 298 Kelvin. Okay, so we've got the basic information, and the question is, oh, and by the way, they are telling you that there are 3 moles of gas, so the N is 3. So you know N, you know R, you know T. And of course, you do know the volume there. You'd have to convert it using this equation or that equation. But anyway, we have all the information we need. And the way it's written, they're trying to lead you to do a calculation. It's not necessary. First of all, you decide that they're determining the pressure. So you convert that to P equals nRT over volume. And then what you do is you look at these and check that the various N's, the R's, T's and volume are in the right place. Now, N is 3, 3, 3, 3, 3, fine, no problem there. R is on the top, 8.31, 8.31, 8.31, 8.31, 8.31. Oh, that's fine. T. Now, T has to be on the top. Ignore that, ignore that. There it is. There's only one. It must be D. V is on the bottom, and there. And you don't have to do that calculation to find out which of these is it. Is it 0.0005 or 500 or what? You don't have to do a calculation. You just look to see if the variables are in the right place. And lo and behold, it's the temperature that actually tells you this is the one. Don't get involved in trying to look at those and understand them and see whether they're correct or not. Just look for whether the variables are in the right place. And I started from the left, you could have started from the right. It would have been so much quicker to start from the right and say T, look all the way down and find, it's only this one. But I started from the left, and N. Okay, that was in the right place, that's in the right place, T. In another question of this sort, it may be that the very last variable is the one you're looking for. It may be if I went nRT, then V, and then I find V is the very one that I was looking for. But in this particular case, T gave us the answer. And if you think about it, this can be done relatively quickly. It doesn't need 90 seconds. It could be done in 20 or 30 seconds. This is an interesting one. There's a lot of numbers in it. Once again, we start with PV equals nRT. PV equals nRT. Now, they're interested in the molar mass. So, we have to change the N, and we know that N, the number of moles, equals the mass of the material, whatever that is, in this case it's 0.18 grams, divided by big M, the molar mass. And so we either substitute for N in there, in this equation, we're using that, or we substitute for N in there. It doesn't really matter. We get to the same thing in the end. Little m over big M, RT, and then we rearrange it and we get M RT over PV. And then we start looking at the numbers and the variables. They've quite reasonably given us the value for R, the gas constant. They've told us that this 1 atmosphere is equal to 1.01 times 10 to the 5 pascals. That's good. And they've told us the mass of the material, 0.18. They told us the volume in centimeters cubed. And you remember in the previous one, I did mention that this V here is always in meters cubed. So we would have to, they're doing the calculation for us, they would have to calculate that into meters cubed. And remember that 1 meter cubed equals a million centimeters cubed, or 10 to the 6, whatever way you want to look at it. And then we look at the temperature, and we realize, of course, temperature is not in centigrade, but it's in Kelvin, and therefore the T is 298 Kelvin. So we've got all the information, we understand it. This little m is the 0.18. And so we do that quickly. All of that can be done fairly quickly, 15, 20 seconds, getting the whole gist of what the question is about and the nuts and bolts of it. Then we look at the values they put into this. And first of all, I will look at M, and the M is 0.18. So they put it in the right place there. Doesn't seem to be in that one. It's in the right place there, and it's in the wrong place there. So we scrub that one and we scrub that one. So we know it's either A or C. And then we look at R. R is there, is there, is there, and is in the wrong place there anyway. So that doesn't help us. A and C have R in the right place. T, temperature, 298. We're looking for 298 on the top. 298. No. Yes. And therefore, this must be it. As I said in the previous question, I started from the left and worked to the right, and then I would go underneath and look underneath. However, it does look as though if you look for temperature on the top, you would get it quickly. Pressure is a little bit unsure. Again, pressure, you'd get it there. You'd find in both of those pressure. And the volume. The volume, you'd have to do this calculation, and I would avoid that until the very end with that kind of calculation. But clearly they've helped you there. They've told you it's 75 times 10 to the minus 6. Fine. And in fact, that and temperature, the volume and the temperature are the only two that are correct. In fact, the only reason for choosing C would be that you could see temperature and volume as correct. And then you'd immediately notice that all the others were correct. There are a number of different ways to getting to the final answer, C. However, it looks to me, since this is the second time that temperature has given us the correct answer, if I come across this kind of question again, I will first of all check temperature, see where that is, and that might tell me the... Now, there is no guarantee, of course, that the examiners will do it that way. They may just decide, oh, let's make it volume is the one that determines the correct answer. We don't know. But temperature is clearly something very easy to look for. If it isn't temperature, then methodically work through the others until you get it. Okay? So the simple method is to, first of all, write down the PV with nRT, and then if they ask you for something like molar mass, work out that and work out the equation for molar mass. When I look at this one, I realize that this is not a chemistry question, it's a mathematics question. Those of you who are skillful in mathematics will realize that this kind of curve, this parabolic curve has the equation xy equals a constant. And you immediately see that as PV equals a constant. And you immediately see it as C. And it doesn't matter whether this is P and that's V, or this is V and that's P. It's the same because it is clearly symmetrical above that, around that line. Now let me show you the other possible curves that you would see in this kind of question. Let me put pressure and temperature there. Let me do the PV equals nRT. If pressure is graphed against temperature, then you're going to get a straight line. If pressure is graphed against number of moles, you're going to get a straight line. Let me show you something else. If you move that around, PV equals nRT times 1 over V. Notice how I put it. I brought the V under there, and it's 1 over V. If pressure is graphed against 1 over V, you get a straight line. By the way, if they change that around, you can put volume against 1 over P, and you get a straight line. So what I'm telling you is that in all the graphs that they will give you, most of them will be straight lines, and only this one has this parabolic curve. And that is due to the fact that PV equals a constant, which means that as P increases, V goes down. As P increases, which let's say it's Y, V will go down. Or if this is V and that's P, V increases, P goes down. So x-axis P, y-axis volume V. C. So let's put the equation down. PV equals nRT. And what is the pressure? So pressure equals nRT over V. And the volume is doubled and the temperature is doubled. So if the volume is doubled, that halves the pressure. Temperature is doubled, doubles the pressure. So therefore the pressure is unchanged. It's 40. And there's different ways of seeing that. You could simply say, oh, well, that is doubled and that is doubled, then they're cancelled out, unchanged. Or you could say temperature is doubled, pressure is doubled, volume is doubled, then pressure is halved again. This is similar to the one before, except it's a little bit trickier with the triple. PV equals nRT. What is the final volume? So V equals nRT over P. What are they changing? Temperature is doubled. Okay, so if we double the temperature, and then keep the N, the R, and the P constant, we have to double the volume. So we're going to double the volume. And then we triple the pressure. So if we then triple the pressure, we then reduce the volume to a third. So it's 2, 3. And that is the answer, 2, 3. So we go back. PV equals nRT. What is the volume of the gas? V equals nRT over P. And the mass is irrelevant. What we're doing, where pressure is doubled. So if you double the pressure, you will halve the volume. And if you halve the temperature, you will halve the volume again. So the volume is now a quarter of the original. What was the original? 2. A quarter of the original? 0.5. Oh, another one. PV equals nRT. V equals nRT over P. So, what are we doing? Pressure is doubled, so that halves the volume. Temperature doubled, so it doubles the volume. So you go back to where you started with. Once again, then PV equals nRT, and they're asking for at what temperature. Right, so we've got T equals PV over nR. So the volume is doubled, so the volume is doubled, therefore the temperature will double. And that is the only way to get P constant. If you've doubled the volume, you've got to double the temperature to get P a constant. So the temperature is 27 degrees centigrade, and we know this temperature is in Kelvin, so it's 27 plus 273 gives you 300. So the temperature has increased to 600 Kelvin. And they say at what temperature in degrees centigrade. So you take off the 273 again, and you get the answer 327. This is one that may take a little bit longer, but it can still be done in 30 seconds. If you simply write that down, rearrange that, and think about the changes in volume, how it affects temperature, and then take into account this simple calculation for converting from, first of all, from centigrade to Kelvin, and then back from Kelvin to centigrade. This is the same. You start with PV equals nRT, and you think to yourself, what is Avogadro's law? Avogadro's law is the relationship between the volume of a gas and the number of moles. So it's just the volume and the number of moles. And therefore, you can see that V over N equals RT over P. And they say P and T are constant, R is a constant, so it's V over N. D. Avogadro's law simply says that the volume of an ideal gas is dependent solely on the number of moles of the material present within it, or the number of molecules within it. If you found this YouTube video helpful, please say you like it and subscribe to my channel, and look at my other YouTube videos. Thank you.